All right. So black hole radiation, Hawking radiation today. And I just wanted to mention at the start, there's sort of two pictures that one tends to see. One, which is what Hawking did originally, was a collapsing star. Which forms a black hole, and then things radiate. You can sort of see the logic of this, because then your in states are things that are incoming states, incoming radiation. That just makes it through the black hole, through the region, and emerges. And so the rays that you see, you sort of trace the rays. And the ones you see are the ones that just emerge, just make it through. See ones that just make it through. And emerge on the other side as outgoing rays. And then there's another set of calculations which are what you'd call eternal black holes. And here the focus is basically you compare the vacuum at near the horizon to infinity. So basically, you compare in and out, and to do that, there's then a coordinate transformation, which is just like an acceleration. So basically near the horizon, good coordinates are sort of like the ones that are free falling in, and at infinity they're stationary at infinity. This is just like the acceleration case. And so you can do that by just doing the same math as the en route case. So I have planned for us 4 derivations, of which 2 are going to have to go. 3 of them have to go quick, and one will be hopefully extensive enough. So let's first just say some things about black holes. The metric, the Schwarzschild metric, is in usual coordinates is 2gm over r dt squared minus dr squared over 1 minus 2gm over r minus r squared d theta squared plus the angular part. So that's the usual Schwarzschild coordinates, and in some things I'm going to call 2gm over r sub g, because that's the notation that the book by Winitsky and Yukhanov do, and that's been a source for some of this stuff. So just to say things that you probably have heard, the horizon is not really a singularity. Horizon is when when the radius equals 2gm and these things blow up, but that's just an artifact of the coordinates. Are you guys still there in Dartmouth?
Yeah, we're still here.
Okay, thanks. I just lost my other computer, so I didn't know if everything got lost.
No.
Okay, good. Thanks. No, RG is 2gm, so this is RG over R. Okay. So when R equals RG, then okay. But if you form the curvature alpha beta gamma delta R alpha beta gamma delta, that's 48 G squared M squared over C to the fourth. I've even copied down R to the sixth. So there's no singularity at the horizon, and in fact, at the horizon. So here's at the horizon. This looks like 3 over 4, 1 over G fourth, M to the fourth. So for big enough black holes, this thing can be arbitrarily small. You just make it big enough, you get a very small curvature at the horizon. The singularity at the origin is, of course, real, at least in Einstein's theory. The wave equation, so we have box phi is equal to 0. That's what we're solving. We would, we're going to do one of the calculations in usual 3 plus 1 dimensions. So for that, we take phi of T R theta and phi and expand it in partial waves. Phi L of T and R, Y L M, theta and phi, so the usual things. And in this case, then the wave equation becomes, and you get the two-dimensional box in whatever coordinates you choose to use. And then there's a piece here which is 1 minus RG over R, RG over R cubed plus the L plus 1 over R cubed phi L T and R, that equals 0. And so what you see is it's basically the 2D problem, which is what I'm going to start with. The 2D problem is just the same calculation we did as for acceleration. And then there's a V of R. This V of R looks like the following. It goes to 0 at the horizon and then peaks out, and then the tail of it is the usual 1 over L plus 1 piece. So what that means is that if you're solving the wave equation here, there's some transmission and reflection coefficients. So if you imagine doing this problem. And so the real result, is there a question there?
Yes.
Yep.
L times L plus 1 term, does that go?
Cube squared. Sorry. Was that the question?
Yes.
Okay. Yes, good, thank you. Okay, so the real result for Hawking is not really black body. It's d omega dt it's 1 over 2 pi. You get the e to the omega over t Hawking minus 1, so the black body part there. But upstairs you actually get some coefficients. The transmission coefficients that take a wave from in here and propagate it through that barrier out. So the transmission coefficient. This is often called the gray body factor. Okay, I'm going to neglect that in the derivation that I do, just because it's a little painful to do.
So this also comes from the
Yeah, so yeah, the Hawking's calculation had it in, for example. Okay, but that makes it painful to do the calculation because then you have to start doing the wave equation through this, and it was never done. To do it completely, you actually need to do numerics. It's not something you can solve, and so there's this. Yeah, the first guy I know that has solved it is a guy named Elster. But anyway, so that's the setup. That's the end goal is right there. I'd like to do the 2D calculation first. The all right, good. So in the 2D calculation, the pathway is basically just finding the right coordinates. Basically, the first thing that one tends to do is to take the dr over 1 minus 2gm over r and call that dr star.
What's the bottom line?
Yes, is that another question? No.
No. No.
Okay. Okay. So basically, getting rid of that 1 minus 2gm over r downstairs by using this coordinate. This is sometimes called a tortoise. And can I spell tortoise? I'm not sure I can. The tortoise coordinate, because as you get close to r, it goes slower and slower. Okay, because the factor gets bigger and bigger. In this, the nice thing about this is that the ds squared now is in 2D. It's conformal at this stage. 2gm over r. It's dt squared minus dr squared, r star squared. Which seems fine, except that this guy still causes us some troubles having it out in front, and so the standard thing is to take one more step. That's a nice step, but the next step is to go to Kruskal coordinates. There'd be T bar and R bar, and I actually don't want to do the derivation. I didn't rewrite it in my notes. It's just something you can look up in a book. But the good features of this are that it looks just like this accelerated coordinate system that we had before. So if you form U bar is T bar minus R bar, and V bar is T bar plus R bar, so the incoming and outgoing waves, then U bar at the center is minus 4gm e to the minus u over 4gm, and u is is t, the original t minus this coordinate, and v is the original t plus this coordinate, this tortoise one, which goes out at infinity to usual coordinates. And v bar is the 4gm e to the v over 4gm. So they have this exponential relation that's just like what we found in Rindler. Okay, but now we're basically done. Okay, remember the action was conformally invariant. Oh, and I didn't show you the metric there. Okay, I need to show you the metric. ds squared in these coordinates. S squared is it's minus 15g squared m squared. No, actually, let's do it this way. It's 2gm over r 1 minus e to the minus 1 minus 2r over 2gm, actually is what it says. Then dt bar squared minus dr squared. So it's still conformal. And that was in, let's just make that a little prettier. This is actually, it's actually R. It's R. This is actually, no, I know. This one is actually the original R. The original R. Yeah, this is R bar squared. Yes. Yes, thank you. So here sorry. Let's get out of this thing. All right. Good. View. Full screen. Okay, there are those guys. Okay. You can write them in the other coordinates too. I have a version that has this, but basically the main feature is that this is very close to 1 near the horizon.
John?
Yes?
We can't see the computer where you're writing on anymore. We're seeing desk. Okay, thank you.
Did it just changed out?
Yeah, now it's back to normal.
Okay. It seems like you have a couple second delay from what happened here. We had the little blip here too. Okay. So this is basic features. This is near 1, like 1 near the horizon. It's nice, well-behaved coordinates, and the action in 2 dimensions, remember, is conformally invariant. Is then integral d t bar d r bar 1/2 d t bar phi squared minus d r bar phi squared is just the usual wave equation, so we know the solutions. So, okay, so at this stage, now we're done. Okay, we're done by analogy. Basically, we've got the same coordinate problem that we had in the Rindler case, the acceleration case, unruh radiation. We had the same coordinate transformations. We had the same free fields. And so if you take the horizon fields and look at them from infinity, it looks like you're looking at them from an accelerating frame. The relative frames are accelerating frames. And so then the math is the same. Basically, the reason I spent all the time in Rindler was that we don't have to do it now. So the analogy is that in the Rindler case, U bar was minus 1 over A e to the minus A U, and V was 1 over A e to the AV. And the temperature, when you compared them, was 1 over 2 pi A. So this is the Rindler case. And the black hole case, then you can do the same thing as U bar is minus 4 GM e to the minus U over 4 GM. V is 4 GM e to the V over 4 GM. And then by comparison, A is 1 over A is, you're right. That solves my next problem. It's A over 2 pi because A is 1 over 4 GM. So here the Hawking radiation is 1 over 8 pi GM. Okay. So, basically what you do here is you go back and construct those Bogoliubov transformation and solve for that. Okay. So that's the derivation that comes out of the Mukhanov-Winitsky book, basically. It's good because we can work it through easily. My next thing would be I want to do a field theory derivation without the Bogoliubov transformations being directly calculated. And this is in a way my more favorite one. There's two sources that I have for this. There's I'll just give you the names of the authors. Navarro, Salas, Olmo, and Parker. Parker is the guy who started this game. And there's a few papers I have put a couple of them up on the website from around 2006 to 2007. And there's also an older one by Friedenhagen and Haag. Haag is a great mathematical physicist, and as is befitting of great mathematical physicists, this one is very hard to read. But nevertheless, you can see once you see the ones by Olmo Parker, you can see how it's going to work out the same way. I'll tell you a little bit about it at the end. Yeah, the basic idea is the following. The basic idea is that we can calculate Green's functions, phi of x, phi x prime, and so it goes through the Green's functions. So these guys, g of x, x prime, are the objects we want to study, and this can be turned into either the flux, which might be T0I, which might be something D0 phi, DI phi, by taking derivatives and taking the coincidence limit. This is what Friedenhagen and Haag did. Or you can get A dagger A out of this by using the inversion relations to turn them into phi. So the number operator can also be written in terms of this, and this is what the other paper does. Okay. And so I'm going to use the pathway of the other paper. And what are the things you need to know? Well, you need to know that we're going to use the outgoing waves in a basis where the mode functions of R, theta, phi, and t for the outgoing waves are e to the minus I omega u. So we're still going to use like-tone variables, square root of 4 pi omega YLM of theta and phi. And the other ones will be written in the same sort of basis. So these are the outgoing ones. U in will be just use some other coordinates, e to the minus I omega v, they call it, square root of 2 pi omega. And this is the incoming. Or so if you're doing this collapse one where you have the waves come in, they go through the collapse and come out the other side, you just use this. Or this is the horizon mode. But in either case, you're basically going to use the same redshift relation. The redshift relation basically is V is a constant minus 4g m e to the minus u over 4gm. And I guess I'm going to adapt their notation because I'm borrowing some of their formulas and it does make it easier. I'll call this 1 over kappa e to the minus kappa u. Kappa then is 1 over 4gm. Okay, so we'll stick it back in. It could have been the u bar in the previous derivations. Okay. Okay, so the pathway is to calculate the following. It's basically, we're going to do this. We want to take the vacuum state to be whatever this in vacuum state is, and we will expand phi in either out or in basis. Okay. So here goes. So the pathway is, let's calculate the number. Okay, the number operators and is going to be, I'm going to take the in states and we'll take A dagger out, A out. So these are the outgoing ones, but taken in the state that's the incoming state, or the horizon state, the state near the horizon. Okay, and we'll just take these things to be I and J for the moment, and then we'll take I equals to J at the end, because there actually is a little divergence associated with I equals to J. We'll just deal with that at the end. Okay. And the way you get the relationship between A and phi, if you remember from back when I did the projection operators, you take a surface sigma mu for one of them, and the sigma out nu for the other one. So that's a surface. You take the outgoing wave function associated with state I. You take d mu left and right on phi, but I'm going to put phi over here. Okay, and I'm going to do the same thing for a dagger, except it's one of these is u star and the other one's u. I want this to be 1 and this to be 2. D nu left and right, acting on phi. Okay, so that was the projection operator to get A and A dagger. Okay, and if you'll allow me to do the following, let's take this guy here, and I'm going to write that as the in phi 2 in minus out phi. Okay, so it's just, okay, now this last term shouldn't really contribute if you do everything right, and in one of the papers they don't bother doing that. I'm going to do it just because it makes a point later on, and this thing should be equal to 0 if you treat everything right. We're going to be a little bit sloppy about the ordering, in which case it's not going to be 0. Okay, so this is not equal to 0 if I'm going to symmetrize the Green's functions in just a second. Okay, so everyone comfortable with that start? Okay, let's call this guy G in, X1, X2, and this guy G out. And we're interested in the difference. Basically, phi between the in vacuum and the out vacuum. That's the particle production. Okay, so that's pretty general. At this stage, we do the following. We go to use these light cone variables. And we integrate by parts. So integrating by parts, I'm taking this derivative that's left and right and putting both derivatives on phi. Okay, this then turns into let's call it Nij. Here, I and J there. Nij is it's going to be 4 because there's two terms in each case times integral du1 d omega 1 du2 d omega 2. So that's my surfaces. U star out 1, U star, no star on that guy, out 2. And then I have du1, du d by du2 acting on this Green's function in minus out.
ING is confused why ING is in the purple.
Yeah, so it's like omega 1, omega 2. Yeah, LMs also, yes. They're going to be set equal to each other, and we're going to get delta, Kronecker deltas in L and M, and a Dirac delta in omega 1 minus omega 2.
So in this, the wave function, if you look at the previous slide, there wasn't a radius there. It was just
No,
simply exponential.
yeah.
R and T plus R. So that's like in the what in the region or something.
This
Right in the asymptotic region.
Yeah, I've dropped the potential part of the thing. So this is, I've dropped the radial potential, and so it's I'm just using the two-dimensional box, and forgetting the radial wave function, and I have a YLM out there. Okay. Well, it's also solving it. It's solving it right near the horizon, also. Okay, as long as I'm neglecting that potential part, because I just get the two-dimensional box conformally. The two-dimensional part is conformal. So that's okay. Now we just have to get through a little bunch of math now, but so that's what I want to do. So the angular parts, just give delta L1, L2, delta M1, M2. So that's okay. Actually, I'm one step ahead of myself. So G out is then 1/2. Here's where I'm symmetrizing. Integral d omega sum over L and M. I have YLM of omega 1 or pi omega e to the minus I omega U1 YLM omega 2 e to the plus I omega U2 plus complex conjugate. Okay, and G in is the same thing, but e to the minus I omega V. Yeah. So it's basically the same thing all the way along. And at this stage, we get the delta, the Kronecker deltas for the L and M pieces. So that actually contributes nothing at this stage. We're left over with let me just do one of them. So if I'm looking at the leftover piece for the out guy of U1, U2, that's the derivative with respect to U1, the derivative with respect to U2 of integral d omega 1 over 4 pi omega e to the minus I omega U1 minus U2. Okay, so that's this piece here, and I've got the g factors right there. This turns into minus 1 over 4 pi U1 minus U2 squared. Okay, so this piece here is just 1 over U1 minus U2. So I just calculated that piece there. That's that's the usual free field propagator for Green's function. For the in one, we take this du1 d respect to u2 and write it as dv1 respect to u1 dv2 respect to u2 dv1 dv2. And so, and then this piece, then acting on G in gives me the same thing. The leftover piece in is the V1 du1 dv2 du2 times minus 1 over 4 pi 1 over V1 minus V2. All right. Okay, so what, okay, I admit that some of the steps there might be hard to follow. They're not particularly tricky though. Basically, I'm just using one set of coordinates here, another set, and my derivatives on the outside are respect to the late time coordinates. Okay, this leads to the following. It leads to the formula that the number operator in Nij in is some factors that we don't need to follow along with. Here's the interesting piece: du1 du2 e to the minus I omega 1 u1 minus omega 2 u2. So these are 1s and 2s here, times a factor which is dv1 du1 dv2 du2 1 over v1 minus v2 squared, and then this one, the outward is 1 over u1 minus u2. Okay. All right. So at this stage, you can see what is in the end the crucial point is that all the action is in the coordinates okay, and this work of just grinding and putting it in terms of the Green's function has just produced a convenient form for the coordinates where you can see everything. Okay, and now at this stage, it's all just calculating this using the coordinate transformation. So v is a constant minus 1 over kappa e to the minus kappa u. D v du is then e to the minus kappa u. So the exponent comes in here with these transformations. And in the denominator there, the pathway is the following. If you change to y is u1 plus u2, z is u1 minus u2, all right, let's just do it enough that you can see where the key stuff comes out. We have d v1 du1 dv2 du2 1 over v1 minus v2 squared is then we're going to take u1 and write it in terms of y and z, and v1 minus v2 then is just going to depend on z. Actually, it's not true. Okay, so I'm trying to figure out, given the time, how much to bother with on this calculation here. The first factor is e to the minus kappa y plus z over 2, e to the minus kappa y minus z over 2 is the second factor. And then the difference down here is 1 over e to the minus kappa y plus z over 2 minus e to the minus kappa y minus z over 2 squared. The factors of y all disappear if you look at this thing carefully. E to the minus kappa y sits upstairs there. You factor out e minus kappa y downstairs. That disappears completely. This just turns into kappa squared e to the minus kappa z over e to the minus kappa z minus 1 squared. So the calculation we're trying to do then is this n1, 2 n is 1 2 pi square root of omega 1 omega 2 integral dy e to the minus I omega 1 minus omega 2 y integral dz e to the I omega 1 plus omega 2 over 2z. And then the factor that I just calculated for you was kappa squared e to the minus kappa z, e to the minus kappa z minus 1 squared, 1 over z squared. Actually, now, I like this particular form for the following reason. You can see at this stage that if I turned off the gravity, so kappa goes to 0 here, that these two exactly cancel and I don't get any particle production. And so really it shows you that all the physics was in this coordinate transformation. All the rest of this stuff is sort of the window dressing that you have to go through. The y integral in this thing just gives me a delta function of omega 1 minus omega 2. The z integral is some integral that you do by contour integration. It ends up giving you, so the piece that I have here with the 2 pi omega 1 omega 2 gives me a factor of 1 over e to the 2e e to the 2 pi omega over kappa minus 1 from doing that integral. So here's where the Planck spectrum comes in. And it comes from that coordinate transformation there. Okay. So given the time, this energy conserving delta function isn't surprising. When we do n total is the integral d omega a dagger of omega a of omega. So these have the same omega. Then the delta of omega 1 minus omega 2, which is e to the minus I omega 1 minus omega 2 times t dt, just turns into t. And so the final thing that I've just derived here is dn d omega dt is 1 over e to the 2 pi omega over kappa minus 1. Here's the Planck spectrum with the temperature equals kappa over 2 pi, which is 8 pi gm. Okay. So I'm sure that this went by fast, but in a way it's a simple derivation. You basically use the derivatives on the Green's function to give you a number operator, plug in your bases, and grind away. Okay, so sorry if it was a little too fast. But some comments about it. All of the action here was in this kappa squared e to the minus kappa z over e to the minus kappa z minus 1 squared minus 1 over z squared. This guy actually tells us some important physics. This is not sensitive to short distance physics. Okay. The short distance singularity of this thing cancels between the two terms there. They both have the same short distance singularity. This function goes like a constant and falls off. So if you were to cut out the short distance piece here, you don't change the integral very much. And so these guys, the guys check this. By actually doing a cutoff, a Planck scale cutoff, and find that the Hawking radiation is insensitive to Planck scale physics. There's a paper on the website by Burgess and Hambley, which I also like, did the same for the other derivation, the Friedenhagen and Haag derivation that I referred to. They deciphered it enough to figure out how to check that it's insensitive to short distance physics. So that tells us that this is real no matter how you complete the theory of quantum gravity. The other comment I just wanted to say associated with this is that the effect comes from the relationship between the horizon and a distant observer and the classic paper by Unruh that we referred to for Unruh shows that an observer near the horizon sees nothing. Okay, at least if you're in free fall there. So if you're living near the horizon, you don't see it radiating. So it's not like there's this little position in space that's giving off this radiation. When asked about it, Unruh says that it comes from, a few horizon distances out. So if you're trying to picture where this thing comes from, it comes from this coordinate transformation, but if it's effectively a few horizon distances where the field is still strong. It's not weak as it is far away, but it's not really coming directly from the horizon. Okay. So perhaps a little too quick, but anyone want to ask questions about that derivation before I try the two others? I don't know if I can do the two others.
You have a question about the interpretation.
Yes, okay.
So if the observer near the horizon doesn't see anything, doesn't that kind of refute the notion of particle-antiparticle creation and then one falling into the horizon?
Yeah, so that's actually the next derivation, and it certainly is in conflict with that, but I think it's probably an observer-dependent statement, an observer-dependent effect. The observer near the horizon is really one who's locally flat, which basically means that he's free falling in.
Yeah.
He doesn't. He sees flat space basically, so he doesn't see any need to be tunneling. I was going to just talk a little bit about the tunneling calculation as my next one, and that is in fact the thing that I don't understand about it, because it seems very coordinate dependent. The actual calculation seems exceptionally coordinate dependent, and in fact only seems to work in bad coordinates. So I would be interested in reframing it in terms of good coordinates, where things are flat near the horizon. Okay, is that enough of an answer? Why don't you wait and let me just talk about the tunneling calculation.
How come the observer near the horizon sees locally flat?
Well,
I mean, if someone's locally flat, the observer has to fit it.
well, but anyone can be locally flat. You know, okay.
Why is anyone seeing any?
Well, so the observer at the horizon doesn't see the horizon as anything special, at least in these calculations. And so it's
nothing to do with flat. It has to do with the idea that the observer is free falling.
Right. It is that, but it means that if you're that observer, you're not seeing anything radiating from the horizon. It's not like the horizon is any place special in this calculation. It's really the relation between the horizon and the distant observer. And in fact, I mean, according to Unruh, the observer at the horizon sees some stuff coming in with him from backscattering off that potential, basically coming from infinity. Okay, that's the storyline. Okay, so let's quickly do Hawking as tunneling. So this was done by Frank Wilczek and Malik Parikh, Parikh. Okay, and the logic is what was said just a minute ago, that vacuum polarization creates a pair, so it's hand waving. One particle falls into the black hole, the other particle moves out to infinity. Okay, then it's a nice picture. In the Parikh-Wilson calculation, they actually it didn't fall out as easy as you might expect. What they have to do is they have to actually account for a black hole with some mass m going into a black hole with some mass m minus omega, plus the radiation moving out. So they have to include the fact that the black hole mass would have to change. Okay, I'm not going to do the whole calculation. It would take too long. But they start off with the imaginary part of the action is the imaginary part of the integral from r initial to r final of p dr. So this is WKB like. They choose some coordinates which are not, as I say, they're not good coordinates, and convert this. So there's ... a bunch of stuff here, but it's not deep calculations of, they turn it into an integral over omega, this emission from R min, our initial to our final, dr of 1 minus the square root of 2m minus omega, there's a g sitting there, over r. Okay, and the reason, so why would you get an imaginary p? Well, you get an imaginary p in this case, not because you're going through some potential that you normally have, but there's a pole here. Okay, so this is the part of the calculation that seems funny. There's a pole because you didn't use good coordinates near the horizon. So I don't mean to insult them. I'm sure they have some rationale for this, but the coordinates have this integrable pole at the horizon. So you put an I epsilon in, and you do some contour integral. The other thing that this recoil is actually a bit strange. So the change in mass is needed, and our initial is actually bigger than our final in their calculation, because as the black hole emits, it shrinks. So you're actually tunneling from a distance out to a distance in. That seems a bit funny, but that's what they do. And they find the imaginary part of S is 4 pi g omega m minus omega. That second omega dependence there is higher order. I don't know how much it can be taken, but this then leads to, gamma is e to the minus 2 ms, and you get the Boltzmann factor out of this. Okay, so here everything takes place at the horizon, so you really are right at the horizon in these coordinates. That's a little bit distinct from the type of calculation we did before, where it doesn't happen right at the horizon. So I'd be interested in trying to see if this thing could be reformulated using better coordinates and consistent with the other one. All right. I guess I will skip the last derivation, which is sort of a Euclideanization of the metric. The other thing I did want to end with some comments on the endgame. Because here is also something I think that hasn't been all that well studied. So the mass, decreases as you radiate. The temperature is proportional 1 over the mass, then goes up, so it gets hotter. So backwards from usual radiating system, they normally get cooler as they radiate. This one gets hotter. this then gives it a finite lifetime. The lifetime tau is proportional to the mass cubed, the initial mass cubed. The scales are set so the Planck mass is about 10 to the minus 8 kilograms. So if you had a black hole of 10 to the minus 8 kilograms, the lifetime would be the Planck time. Okay, and then you scale up by as m cubed. So it lives longer. But the description when you hit when m gets close to m Planck, the black hole description changes. And there's not been a lot of investigations of this. There's a recent paper by Liu, Perkins, Pope, and Stelle. So this is 2015. And there's a very good paper by Bob Holdom, 2002, that says this basically the same things. And I don't have time to say much about it, except that these papers here now include the R-squared effects that live in the effective Lagrangian. And what they show is that there are extra solutions. There's some with no horizon. Some with two horizons. There's some with no singularities. So these are all the possibilities. The end stage is not certain at all from this. So the statements that the black hole actually separates is not at all clear. It may actually lose its horizon as you get to the end game. That's the letter. They haven't included all the. So yes. So this is a letter. However, I have the advantage of having heard a talk where I've heard more of the details and discussing it with Stelle. And I know that they confirm Holdom's paper from that conversation, and Holdom has some of these effects in it already. Okay. All right. So I don't know. There's always more to say. I'm going to have to stop here. This is just an introduction, more to be understood, but this is the end of the course then. Thanks. Okay. Bye-bye, guys.
All right. Bye, John. Bye. Thanks.
All right.